This is my milling machine. It's like a beefcake drill press that cuts metal in 3 axes. Front, back, left, right, and up and down. You do so by turning those hand wheels you see by the table and the top. Now, I'd like to add some motors to it. These motors will replace the hand wheels and allow me to do stuff more automatically. I'll control the motors with drivers. Those take impulses from a breakout board, which has sent data from a computer. Combine this together, and we get TNT! The machine I'll be converting is called a G0704, as sold by Grizzly. It's imported by other companies under other names, and it's a popular candidate for CNC conversions because it's got a large work area and a square vertical column. I've had this milling machine for just over a year and been using it in manual mode. To be perfectly honest, an essential upgrade for it is to make some leveling feet. I'm using some 3-inch cold-rolled steel here with 1/2x13 all-thread. The all-thread will go through some holes I drilled on 4x4 studs. I can bolt the studs to the stand and then adjust the height of the feet with nuts. This little chore is pretty necessary. I should have done it a long time ago. It also lifts the mill to a usable height for a tall guy like me. Now let's talk about the rest of the project. So what do we need to turn a manual machine into something computer-controlled? Well, on the electronics side, we're going to need motors, drivers that run those, and a breakout board that intercepts computer signals. I got a kit that contained all of those from eBay. It's Chinese. It's a company called Long's. These are NEMA 34 motors. They have 1,600 ounce-inch holding power. Stepper motors move just 1 step at a time, and these move 1.8 degrees per step. That's how you can get a lot of precision control and a lot of strength out of them. The next part we're going to need are called ball screws. Yes, you can laugh. Ball screws replace the Acme screws inside the machine that control the motion of the table and the head. Ball screws are a ball bearing race in the shape of a helix. They allow for incredibly smooth operation and almost zero backlash, which is the lost motion when changing directions. You can convert a machine using its existing Acme screws, but this is a huge upgrade. I got these ball screws from Automation Technologies. They are specifically made to fit this machine using Haas's conversion plans, which I am. These are double nut ball screws, which take an extra step to minimize backlash by incorporating a second nut attached to the first. There are also bearings and motor couplers we'll need. Those are outlined in the plan set if you buy that from Hoss. Now that brings us to a huge part of this project, and that's making the mounts to get all this stuff in and on the machine. I purchased a set of plans from Hoss, aka Hossmachine on YouTube, and his website, G0704.com. The designs for all these mounts are his product, so I won't share any numbers or measurements. His designs do call for smaller motors on the X and Y axes, and I had to modify the designs to fit my larger motors. I also modeled up all the parts in Fusion 360 because, well, why not? Machining the mounts for the motors, the ball screws, and the bearings is pretty straightforward, and it's great practice of a lot of standard operations on the manual milling machine. The stock is squared up to dimension, and then accurate holes need to be laid out and drilled to size. Boring operations are done on larger holes. Now, that was my first experience using a boring head, and it took me to school a little bit, but I eventually got it pretty well figured out. While most of the parts were made out of aluminum, I made the standoffs for the motors out of 4140 steel. And that's mostly just because that's what I had on hand. Making all these mounts took no small amount of time, so I understand why people who sell these conversion kits ready to go charge so much money. And like I said, I'm using Hossmachine's plans, which are fine, they work really well. It wouldn't be difficult to design all these parts yourself if you were really motivated. There's also our friend Aaron down in Australia of the YouTube channel DCT Teacher 1. And he's designed a set of conversion parts for this machine that he's shared for free, so go check out his channel. It's pretty interesting. He's also done this whole conversion. With all that fabric cobbling done with, let's take the machine apart. Now, having recently rebuilt a South Bend lathe from the 40s, I can tell you, breaking down another machine isn't super appetizing. Luckily, this isn't a wildly difficult procedure. Taking the head off, and more specifically putting it back on later, is about the most unpleasant part of the entire job. And really, it's not that bad. Starting from the top down, parts are pulled off the machine so that the ball screws and their mounts may be installed. The Z-axis, which is up and down, is first, followed by the X-axis, which is left and right. These side plates hold the table onto its lead screw, and each side has a set of thrust bearing under the hand wheels. They were a little stiff to remove, but not too bad. Unscrewing the entire lead screw for the table probably isn't the most efficient way to get it off. The Y-axis, which controls forward and backwards movement, is the last to come off the machine. With a bare-naked milling machine, this step is done, and we can now move on to getting the new bits and pieces installed. Unlike the lathe rebuild, I didn't null my parts out as well. Oh well, a proper mess such as this means, well, everything's ready to be assembled. The Y-axis block needs to be modified to make clearance for the X-axis ball nut. It would be very handy to do this job in a milling machine, but, well, mine had a bad case of being in pieces. So I used the best friend a metalworker ever had. The dimensions of this cavity are also laid out in the plans I purchased. It can be made a number of different ways, such as with a drill press or a Dremel tool. Precision really isn't necessary, it's just making space for the new part to fit in. This block has a little recess cast into it, and I haven't seen that in pictures of other 704 mills. Now that recess actually made this whole job a lot easier. Once the grinding's done on the cast iron, that tremendous mess needed to be cleaned up, so I used mineral spirits and a brush to make sure that the part was clean. The second permanent modification to the machine was to drill and tap the two holes that hold the X-axis motor mount in place. These are lined up from the mount itself. A transfer punch is used to place center points at each hole. The Y-axis ball screw will be the first to go into the machine. To fit it in place, we'll need to remove the ball nut, which is precarious because that, well, could allow for the bearings to fall out. So to do this, I turned a piece of aluminum down to fit inside the nut and hold the bearings in place. After making this, I discovered later that there was actually a file in the plans I purchased to 3D print this exact tool. That ended up coming in handy later in the process. Tension was high as I went to remove the nut from the ball screw, and panic did set in a little bit when I lost control of the two pieces of the nut. Luckily, the ship was righted, and the whole assembly got put into place. The bearings are set into the Y-axis bearing block. Now, these are angular contact bearings. They're designed for this sort of motion and load. They're lubricated with this special and expensive grease. It's what the plans called for. It seems to be recommended pretty strongly in the DIY CNC community. Beyond that, I'm not sure what makes it so special or expensive. The bearing block is then put in place. It mounts in the existing holes that the handwheels bearing block used. They get tightened down to the lead screw, and then the motor mount itself can be installed. It's right here where I came upon an issue. The ball nut was actually backwards, and it's in danger of being threaded off the screw in the full range of Y-axis travel. The Y-axis had to be disassembled again. And with lessons learned from last time, I taped the two ball nuts together so I wouldn't have an issue with them coming apart. I 3D printed the ball nut tool that I'd found in the set of plans I had, and then used it to help me reorient the nut and get everything correctly in place. Now, the way that the tool is designed, it puts the nut back on the screw in the same orientation as when it came off, and that means I needed two of them to change direction. This also means that the nut came this way from the supplier, which is something to look out for if you're doing this project. The nut being oriented correctly gave me the full range of motion in the Y-axis, and I could proceed to mounting the motor. The X-axis motor mount is put in place. I decided to use grade 8 bolts to hold it onto the end plate because I'm paranoid. I also machined a pocket you can see along the top of the motor mount to give me clearance for grade 8 bolt heads for holding on the motor standoffs. The bearings are sat in the original thrust bearing pockets, and expensive grease is once again applied. And the ball nut and table assembly are all put into place. Lastly, the Z-axis gets the exact same treatment. Bearings, fancy grease, ball screw, and the mount I machined. And getting that mount screwed onto the ball nut itself was a little bit challenging. I could have used about 4 or 5 more hands, but we got there. The saddle for the mill head is slid into place and screwed to the bearing block I machined. With this done, the mill head itself can be reattached. Now, I edited out a lot of this process, but this took me a solid 15 minutes of fiddling to get those 3 bolts lined up to the holes in the head. With the head finally reattached, the machine itself is done. We now turn to the need for a case to hold all the electronic components that are going to be driving this machine. I designed a box to hold everything in a manner that made sense to me. I'm making it pretty basically with a small panel of 1/4-inch plywood. I know my woodworker bros will point out that this is better done on a table saw, but I don't have one anymore, so I just use this little bandsaw I have. The box is mostly for containment and doesn't really need strength. I'm using glues and staples from an air stapler to stitch it all together. Please don't judge me, woodworkers. After a few coats of NASA paint, I prepared the plexiglass lid. With a relatively ridiculous setup, I could heat bend the plexi over the top of the box to match its contours. I was actually surprised how long it took for this thin plexi to get soft and bend. I was using a heat gun that had plenty of oomph to it, and all in all, it still took over 20 minutes of direct heat before we got to the final shape. A piece of piano hinge is cut to length and then epoxied on. The box is drilled for the motor couplers. These are called airline connections. They're a 4-pole connection that screws in. They're pretty handy. The plexiglass lid is then screwed into place. This hole is being drilled for a USB connection. I'm using a USB smooth stepper board as a bridge between the host computer and the parallel connection on the breakout board. The kit came with 3 power supplies, one for each motor. I'm not sure if it's necessary, but I utilized all 3 of these and mounted the drivers vertically above each of them to take advantage of their built-in cooling fans. The breakout board and the USB smooth stepper were also mounted in place in the box. Everything being mounted in place in the box meant for the long process of wiring. Manufacturer of all these electronics actually have a pretty decent wiring diagram, which helped a lot because I really don't know what I'm doing when it comes to this sort of thing. The drivers and breakout board need 5 volts DC for various things, so I hooked up a USB charger to a bus bar and connected that to all the individual components. I soldered in the connections for the motor connectors and realized I should probably have taken them out to solder them in. It would have been a lot easier, but lesson learned, and I got those heat shrinked in as well. I wired the motors up to a 4-conductor cable, as well as the corresponding plug. It is a little bit on the thin side, so I may upgrade it in the near future. Fans of H.R. Geiger will really like this cable wrap to keep everything in place. With everything hooked up, let's turn on the juice and see what happens. The controller software I'm using is called Mach 3, and it's pretty common for DIY CNC. I'm still trying to optimize all my settings with the motors and such, but I've already come a long way. I'm not married to the software. I may consider another controller option in the future. I was able to get some pretty cool movement out of it right off the bat. Had to go back for that L, though. Now, suffice it to say, one of the most important parts of this entire project is making sure that the machine is accurate, and that is actually timing the software with its pulses for how far the machine actually moves. And this was kind of fussy. It did take a little while and a little bit of fiddling. After getting that dialed in, however, I could move on and remove all the control apparatus for the quill of the machine, and gave it a custom faceplate I 3D printed. Now to give this thing a test, I worked up some basic G-code in Fusion 360. Just a facing operation and then a helical interpolation, just cutting a circle. Tragedy struck when I realized I didn't bolt my head down well enough. After getting reset, we were back at the races, and everything seemed to go pretty smoothly as far as the facing operation. The circular cut started off fine enough, except, well, took too big of a bite, broke the tool. For funsies, I tried the exact same program with a larger tool, 3/4 inch instead of a 1/4 inch. It cuts like crazy. It's pretty cool. I would call this, well, more or less successful. The CNC conversion at this point is satisfactory, but not entirely complete. I still want to make sure that the motors and the controls are dialed in to their best potential. I also have a number of plans in the immediate future for things like, well, like limit switches, a coolant system, a belt drive for the spindle, a spindle motor upgrade, a 4th axis, a Y-axis expansion, and any other kind of upgrades I can think of. Now, a subject that comes up with this sort of conversion is that can you still do manual operations? Well, the motors I got are dual shaft, and I 3D printed this little handle, and with power disconnected to the motors, yeah. This was such a fun project to do. I've been wanting to do it for so long. I'm excited for how this expands my capabilities in the shop and the projects that I can do with this machine from here on out. If this excites you as well, hit that subscribe button. Also check me out on Instagram. My regular followers will recognize a lot of this as I've been posting updates on this project for the last 2 months. If you'd like to see my videos a day early as well as get monthly shop update vlogs and a sticker, check me out on Patreon for as little as $1 a month. Anyway, thanks for watching.